Hey.
Hello.
Parker?
Yes. Can you guys hear us?
Yeah, we got you now.
All right. Cool. Well,
we had a lousy hookup or something, but I'm good to go now.
Okay. Guys, you'll have to project clearly and loudly and towards the microphone, okay?
Okay, you guys going to ask me questions or what?
Yeah.
Ask me some questions. What have you just studied?
So you said that enough sunlight falls on the Earth in 1 hour to power the Earth for a year, right? On your website, I think.
Yeah, that's right. Now there's enough sunlight to run the planet. Now it used to be an hour. Now it's an hour and 20 minutes because we need more energy now.
Do you have a plan on how to get energy?
So we just have to convert it to something useful, and of course you know that one way is to get photovoltaic solar cells and make electricity, but we can only use that about 5 hours a day. So what we've been trying to do in my program is to make fuel from sunlight and water. And you may want to ask about that.
What's your plan to make fuel out of sunlight and water?
Well, we've recruited a whole bunch of people around the world to work with us on this. We have groups at Harvard and MIT and Stanford and Caltech, UC Davis, Chicago, all working on different aspects of it. We have to develop light absorbers, semiconductors that absorb all the sunlight that reaches the Earth's surface, filtered by the ozone layer, and then we have to take that semiconductor sunlight combinations and couple it to catalysts, because you have to have catalysts to make hydrogen from water, and you have to have catalysts to make oxygen from water. So the idea is to take seawater and make devices that will convert it into hydrogen fuel and oxygen. And we're well along on that. We have a lot of people working on it. We've developed a lot of new catalysts that work well for hydrogen production. We have some really great catalysts that make oxygen from water. They don't work well with seawater yet, so that's a big challenge, because seawater has lots of stuff in it, like salt and so on, and our catalysts have a hard time working with just seawater, but we're making progress on that. What you ought to know, though, is that we have hundreds of kids your age. How old are you guys, by the way?
25.
16 to 15.
25.
25?
No. 16
You guys
to
look, well, you look like you're about 16.
We are. I thought it was going to go 12.
Are you guys about 16 or 17?
Yes, sir.
Okay, you're just what I need. We've got in my program, we have about 1,000 kids your age, all over the world, working on catalysts, new catalysts for our program. So we call this our solar army. And somebody in the back is waving at me. All right, good. And these kids, we've got a setup. We've got a set up a sort of solar army kit, where kids after school, high school students after school, can check on light absorbers and catalysts. They are making them in their high schools and checking them out and reporting results on the web. And we take these results. They're finding out, for example, that if you put something like yttrium, you ever heard of yttrium?
Yeah.
No. Well, have you heard of rare earths? rare earth elements like lanthanum and cerium and stuff like that. Well, what our high school students have found, if you put these rare earth elements in some of our catalysts, they get a lot better. And so we take these ideas from kids your age, okay, from all over the world, and we have a very fancy laser method to make materials called pulse laser plasma synthesis.
No, this is just a long talk.
Device, it sounds like a machine gun. We blow it up into a plasma that the temperature is about 70,000 degrees. It cools rapidly into nanoparticles, which we use as catalysts. But the important thing for you guys is we're getting lots of good ideas from students your age. So you ought to check our website, look into our Solar Army stuff, and see what we're doing. All right, what else is going on? Parker said you guys have studied VSEPR.
Yes.
Vespers, right?
Yep.
What do you know about Vesper? You know everything you need to know about Vesper? You know that, so what's the structure then of SF4, sulfur tetrafluoride? What's the structure of SF4 by
That's 34.
Vesper? What is it? Huh? No, it's not. It's not.
34 electrons.
Come on, give me an answer, guys.
Trigonal pyramid.
No, it's SF4 for God's sakes.
I'm gonna feel that jump on one day.
Yeah. Come on, do it right now. I want to give you some problems. If you can't do SF4, I'm hanging up. I'll get your pens out, get your stuff out. I'm going to give you some problems.
What?
That's SF4.
What are your questions?
Now I know, but I'm going to ask you guys questions. What is the structure of SF4? Give it to me. Have you heard of a seesaw or sawhorse?
Oh, seesaw? I was going to say T-shape or seesaw.
It's a sawhorse or a seesaw. You know, who's the guy in the front there with the yellow shirt? Who are you?
Quentin.
What's your name?
Quentin.
What?
Quentin.
Oh, Clinton. Nice to know you, Clinton. Now, Clinton, you were right in one way because you put in the lone pairs. It sort of looks like in a one way it's a trigonal bipyramid, but then if you look at it with just the fluorines, it's a sawhorse.
Okay.
Did you guys, or a seesaw? It looks like a seesaw or a sawhorse.
Yeah.
Did you guys must have done that one?
Yes, sir. Well,
That's one of the most famous ones to do by Vesper.
Mr. Singleton.
And then there are a bunch of things that don't work by Vesper. For example, if you know what tellurium is? It's an element. You guys got a periodic table there, or what's going on?
Oh, never mind.
Wait, what element is it?
Tellurium. Look up tellurium for God's sake.
What are the letters?
6.
Tellurium goes oxygen, sulfur, selenium, tellurium. Okay.
Yeah, I see it.
All right. Now put 6 chlorides on tellurium.
Come on, Clinton.
Put 6 chlorines on tellurium. So make
Alright.
TeCl6. Come on, Clinton, get on the ball.
Come on.
Come on, Clinton. Come on, Clinton. Harder. Like a molecule for me.
No.
Put six chlorines around, chlorine atoms around tellurium. Okay? And put in, and make it a 2- anion.
Oh boy.
Make it 2- anion. Okay, so the formula is TeCl6 2-. You got that?
Yes, sir.
Don't call me sir. I don't like that. Call me Harry.
Yes, Harry.
Okay, thank you, Clinton. I'm known all over the world as Harry. Nobody calls me doctor. Nobody calls me sir. Everybody calls me Harry.
We have a Harry in here.
If you go around the world and say, I just talked to Harry, and there are a bunch of chemists there, they'll know who you're talking about. Okay, I'm like Madonna, and I've got one name, Harry. You probably call all these famous professors or something by other names, but don't call me that.
If I go somewhere,
So Clinton, Clinton, have you got this thing written down?
I have the formula and I have the skeleton.
Now what is you know what oxidation states are? Have you heard of that?
I've heard of it. We went a little bit into it.
Yeah, well, tellurium is an oxidation state 4. It's tellurium 4 and 6 Cl minuses. So 6 minuses and tellurium 4, that makes the anion 2 minus. You got that?
They have not done oxidation states yet.
It's okay, I'll teach you right now. It's okay, I'll teach you oxidation states. So if it's TeCl62 minus, then what is the oxidation state of tellurium that would make the whole anion 2 minus? It's obviously plus 4, right?
Yeah.
Because the chlorides are all minus 1. Come on, this is simple arithmetic. Get with it, man. Come on, Clinton, come on.
I'm trying my best.
So it's now now you've got it. Now what I want you to do by VSEPR is predict what the structure is of TeCl62 minus. What is the structure of it?
What is the structure?
By Vesper.
Octahedral?
It's octahedral. Who said it was octahedral? It's octahedral. You got it.
Yes, we all.
Now you can talk to Parker, because I'll tell you, if you did Vesper right, you wouldn't predict it was octahedral because it's got one lone pair. Tellurium 4 has one lone pair and 6 chlorides. So that's 7 pairs. And so that would make it distorted octahedral. But the fact is, it's octahedral. It violates VSEPR. Horrors! It violates VSEPR.
Wait.
It's a famous case. Now I wrote a paper on this many years ago. I explained all this. I want you guys to see if you can find my paper explaining why this anion violates VSEPR. And if you find my paper in the literature and send me an email that you found it with the reference, I will write you back and send you something or other that might be interesting. I don't know what, but I'll find something. Okay? Is that a deal?
Yes, sir. That's a deal. That is a solid.
I told you not to call me Sir, Clinton.
Yes, sir.
Okay, all right. So what are you guys studying today? Today is this called Cool Fridays, right?
Yes, sir. Yes, sir.
How many people have you talked to? And tell me that I'm the most interesting guy you've talked to.
We talked to, what's his name? What was his name?
How many people have you talked to?
Roland Hoffman.
Roald Hoffman, he's very famous.
Yeah. And we talked to,
He's very famous, but he's not very funny. Well, many years ago, Roald Hoffman and I did very similar things in theory. We both worked on development of something called molecular orbital theory. And he went one direction and I went another direction. And I went back to experiment because he's very, very smart, and I decided I didn't want to compete with him. So I went back to experiments, and I've been doing experiments ever since. But Roald is a really great guy. Have you all met him in person or just by Skype?
Just by Skype.
Just by Skype?
Yes, sir.
So I've forgotten where you are. Where are you? Who's yelling at me at the back? Somebody's yelling at me at the back. Everybody's waving, and I don't know what. It's crazy. What?
South Carolina.
Oh, you guys are in South Carolina?
Yes, sir.
Oh, that's why you're calling me sir.
Yeah. Pretty much.
I didn't realize you were in South Carolina. What city are you in?
Charleston.
What?
Charleston.
Oh, you're in Charleston. That's a wonderful.
That's better.
That's a wonderful city. I love Charleston. Now it's better. I've got light. I can see you guys in the back waving at me. I've spent a lot of time in Charleston. I love the city. It's wonderful. You guys are very lucky. You all live in Charleston?
Yep.
And now, what is this a high school or a college? Where are you guys?
High school. High school.
What? Is it a high school? You guys are in a high school?
Yep.
I didn't. Parker didn't tell me everything. Where's Parker? Where's Parker? So is this a public high school or a private high school?
Charter.
It's a public charter.
Private? It's private. So you guys are all rich. No. You're a bunch of rich South Carolina kids.
We're like,
No? Okay.
we're like
So
a
how
fancy
much
public
does it cost? How much does it cost to go to this high school?
We're a public school. We're like a public charter school.
Oh, you're a public school. A public private school?
Hey.
All right.
Yeah, quiet. So, all right, Quentin, tell me.
We're a public charter school.
Oh, public
Charter.
charter school.
Yes.
A public charter school.
Yes.
Oh, okay, that's cool. So, have you taken physics?
Some people are, like for an elective course, but not all of us are.
Okay, well, chemistry is much more fun than physics.
Yeah, especially with Mr. Singleton as our teacher. It's really fun.
Yeah, well, Parker seems like a really cool guy to me.
Yeah, most of the time. Most of the time.
So, is this course that you're taking boring or not?
Not really.
So you like chemistry. Let me ask you guys, when did you start getting interested in chemistry?
This unit, I like this unit. Yeah, like this unit was more fun. It's more hands-on, so you can like do more.
Do you guys do lab experiments too, or just huh?
Yeah.
What do you do in the lab?
We did some Bunsen burner experiments. We did some with what was it? Oh yeah, we set flour on fire. Like you breathe through
You
this.
set what on fire?
Flour.
Flour.
Yeah. So he like lit up a Bunsen burner, and then like he had a big funnel, and then he'd let the flour down, and then it just kind of like go out like a flamethrower.
Have you guys made a solar cell yet?
No, I really want to.
Why don't you make a solar cell out of blackberry juice?
Can we, Mr. Singleton? He says yes. He says yes.
We can, Siddharth is here with me. We can teach you how to make a solar cell out of blackberry juice.
Okay. All right. Yeah.
So we'll send you some information about it, and I want you guys to make a solar cell out of fruit juices. You can make it out of blackberry juice. You can make it out of pomegranate juice. You can make it out. There's all kinds of fruit juices that have compounds in them that absorb a lot of sunlight. They're called dyes.
Okay.
And these solar cells that we make are called dye-sensitized solar cells, and they pick up sunlight and they make electricity. And you can make them in your class. I think it'd be a great exercise for you guys. Parker, where are you? Parker?
He's coming to the front.
Parker?
Yeah, Mr.
Oh, there he is. Parker, what do you think? Is it okay? Can you guys make how about making a solar cell for me?
Yes. We can
And
do
then
it.
I'll come back on later and we'll talk about it.
Okay. Today?
No, not today. No.
Okay. Yeah.
How long is this course going to go, Parker? All year?
We finish in early January.
Early January.
Yeah.
I tell you what, I'll give you an assignment to make a dye-sensitized solar cell. I'll let you guys test it, and I'll come back on in early January and we'll talk about it. How's that?
Sounds good to me. What about you guys?
Is that a good deal? Clinton, is that okay?
Yes, sir.
All right, well, we'll send you I don't know what the hell you're looking at, but you're looking at something up there. I don't know. You looking at me or what?
Yeah, I'm looking at you.
Okay, good. All right, Siddharth, can we do that?
Yes.
We'll send you directions on how to make a dye-sensitized solar cell just out of simple fruit juice and stuff. And Parker will probably figure it out. And Clinton, I'm deputizing you, Clinton. You're the head of the team, Clinton.
Yes, I'm in front of all of you. Yes, thank you.
You're head of the team, and if you don't come through, Clinton, I'm coming out to South Carolina, and I'm going to find you, and I'm going to track you down.
All right, I won't let you down, I promise.
All right, don't let me down.
I won't.
So we'll send you the info, and if you have any problems, you can email us. Between now and January, you can email us and tell us what your problems are. We can help out.
Okay.
And so that's a deal, okay?
All right.
Now, Parker, what were you going to talk about today before I came on and ruined your whole class?
We're reviewing for our test on Monday.
Oh.
Can you advocate us? Or advocate
What's the test going to be on? Vesper?
So they have Lewis structures, they have ionic versus covalent bonding, polar molecules, Vesper, and some intermolecular forces.
Oh, you guys. Well, you know the difference between covalent and ionic bonding.
Yep.
So I'll give you two things. Sodium chloride, is that ionic or covalent?
Ionic.
Who said ionic? Everybody, hold up your hand and said ionic. Ionic is right. What about methane, CH4? Covalent or ionic?
Covalent.
Right. Parker, I think they're smart. Don't give them the test. You guys just made 100% on my test.
Yep. Hey, you gotta do that. You gotta do that for us.
Methane is covalent and sodium chloride's ionic. Now, I'm very famous around the world for something called the oxo wall. I want you guys to see if you can find out about the oxo wall. Okay? And Parker, I bet Parker doesn't know about the oxo wall. Parker, you know about the oxo wall?
No, sir.
Call me sir. All right. Well, I tell you what. See if you guys can find out what the oxo wall is. It's a big part of chemistry, and see if you can find out where is the oxo wall in the periodic table. See if you can. There is an oxo wall between elements in the periodic table. See if you can find out where that is. And Clinton, pay attention.
I am.
But between now and January, I want to see if you can find out where the oxo wall is, and we'll come on again. Siddharth and I'll come on again, and we'll check in with you in early January. Parker, when's the course over exactly?
I think it's January 15th.
Okay, so we can come on before that, right?
I'll send you guys an email and let you know. For sure.
Send us an email and we'll follow up.
All right.
So we've got I gave him 100%. So give him extra credit, Parker, for getting covalent and ionic. Okay, give him a break.
Please.
And listen, you guys. If Parker doesn't give you a break, send me an email.
Got you. All across.
You get extra credit for my 2 questions. One more question. HCl, hydrogen, HCl, covalent or ionic? Polar or non-polar? Polar or non-polar? Polar, right. That's 2 more.
Yep.
Parker, they made 100%.
Give us some extra credit, Parker.
Parker, they don't need the test, Parker.
Yeah. We don't need it at all.
Parker, what they need to do is start working on that dye-sensitized solar cell.
Yeah.
Okay.
And also, look up the OXO wall. If you guys can find the OXO wall, then that'll be wonderful.
Maybe a good extra credit.
Yeah.
Extra credit to find the OXO wall.
Yep.
So all right, that's it for me. I'll see you guys in January, okay?
Bye. Bye, Harry.
All right. Thank you, Harry.
Bye-bye. All right, we're off.